these things you learn in the first or the second year of your BTech. So there are 2-3 methods, commonly used methods for calculating deflections in elastic systems, right? So there are some methods which are directly applicable to only flexural systems like beams, etc. Then there are some which are applicable to for calculating deflections to trusses, right? First we will talk about some flexural systems. So this is an example of a beam, and I had mentioned this thing the last time. So the method is known as double integration method, and then there are a couple of variations of double integration method. So I will not spend time. I don't want to spend much time on the double integration method as such. Of course, the example is solved here on slide number 22 and 23. I encourage you to go through it, but I don't want to spend time because it's mostly mathematics. You have to just, depending on, you draw the bending moment diagram and look at the bending moment diagram. If there is any discontinuity, that is, you cannot define the bending moment diagram with a single equation. So around this point, where part 1 and part 2 meet, there is a discontinuity in the bending moment diagram. So you have to solve, or you have to write the differential equations in 2 parts. So for part 1, you will write an equation for y double prime, then you integrate it once, you will get y prime, then you double integrate it to get y. Okay, and in the process, you will add these 2 arbitrary coefficients, C1 and C2. Likewise, the same exercise you repeat for part 2, but for that, first you have to get the bending moment diagram, of course. Then you repeat the same exercise, and then you will get 2 additional arbitrary coefficients, C3 and C4. Then you enforce compatibility conditions or boundary conditions. Okay, so now if you can see here, I'm just a few steps here, how I got the bending moment diagram. This I'm sure you already know how to develop. So I'm not going to spend much time on that. Let's say we got these equations for y for the first part. The first part is this part, 2L length, and the second part is of L length, this one. So for the first part, I got an equation for y, which is y is equal to px cubed by 12 minus px cubed by 12 plus c1x plus c2 divided by ei, the whole thing divided by ei. And here, for the second part, y is equal to px cubed by 6 minus 3pl x square by 2 plus c3x plus c4, the whole thing divided by ei. Okay, so straightforward. Now, from here onwards, we have to solve for C1, C2, C3, C4. If we can get the values of C1, C2, C3, C4, we will get the deflection everywhere, correct? Now, how do we do that? So there are 4 unknowns, right? So how many equations do we need to solve them? We need 4 independent algebraic equations to solve for C1, C2, C3, C4. Okay, and those 4 equations will come from 4 boundary conditions. Can somebody tell me quickly which boundary conditions will be applicable? So here, by the time I came up with this y equals to this one, I have not enforced any boundary conditions yet. All I have used are the moment diagram values, okay, bending moment diagram values. So I have not enforced any boundary conditions, that is displacement and rotational boundary conditions. Okay, so the boundary conditions that I can use now should not be on the curvature, because that I have already used. I already used the values of curvature. I know the value of curvature everywhere. Okay, so the boundary conditions that you are going to have to suggest should not be telling me the values of curvature. They should be telling me the values of somebody?
Slope and deflection.
Slope and deflection. Very good. Yeah. So those are the 4 additional equations I need, right? So if you can tell me the value of curvature, that anyway is satisfied here, because that's where I started from. So that's not additional information to solve these equations. Fine. Very good. So slope and deflection. So which slopes do I know the values of? Do I know the value of slope anywhere?
No, sir.
Okay, wait a minute. Let me start from a simpler question. Do we know the value of deflection anywhere?
Sir, at x equals to 0, deflection is 0.
Yes, at x is equal to 0, this is the x value. So at x is equal to 0, deflection is 0, and x is equal to the other one?
12. X equals to 12, deflection is 0.
Correct. So I got 2 equations. One is deflection is 0 here and deflection is 0 here. Okay. Now, if you look carefully, deflection being 0 here, is it only one condition one additional information, or there are two information that the deflection is 0 here?
And slopes also 0, sir.
Slope is not 0. If I draw the, let me draw the deformed shape. This is the beam. Okay. Due to this load, the beam will deform this way. Maybe I should give you guys an exercise to draw the approximate deformed shape also. Yeah. So at the mid support, this is the deformed. So at the mid support, the deflection is 0. That is given here automatically. Obviously, the deflection will be 0, but slope will not be 0. Okay. So deflection here is 0. That is one equation. Deflection here is 0. That is another equation. But is that only one equation here?
Sir, it can be applicable on part 1 equation and part 2 equation as well.
Exactly. Right. So since I am treating part 1 and part 2 separately, there are like so. So I can use the same information in the two parts separately. So basically I get two equations. Delta is equal to 0 and delta is equal to 0. From looking at this side and looking at this side at the same location. Okay. So I got three equations. One more equation I need. Which equation will that be?
At x equal to L, slope is 0. The first part.
At x is equal to L, the slope is 0. How do you know that? See, if I look at the bending moment diagram of this part, it is not a uniform bending moment diagram. What that indicates to me is that this slope θ1 and this slope θ2 need not be equal. I mean, the way I have drawn it, it might give you that impression that θ1 is equal to θ2. But if you imagine only this part, you can also approximate it as, let me draw it here. So this is the beam. This is 2L length. Okay. And I'm applying a moment here. If you are applying a moment here, the deformed shape looks somewhat like this, or the opposite of that, sorry. And moment here, this way. So the deformed shape will look like this. This angle will typically be half of this angle. This will be θ1, this will be 2 θ1. Okay, so that similar situation would arise here. There was θ2 actually in this particular case, if you actually calculate it, will turn out to be twice as much as θ1. So there is, and even if you don't know that, even if you can't think of all this, there is no reason for you to assume that θ1 and θ2 are equal. Or in other words, there is no reason the deformation here will be symmetric. If the deformation is not symmetric, there will be some point along the way. Like in this case, there will be some point along the way where the slope is 0, but you don't know where is that point. What is that x? Where the slope is 0. That is not necessarily at midpoint. Okay. Did it make sense what I said? So it won't be really in the midspan. Anybody else?
Sir, θ2 in part 1 is equal to θ2 in part 2.
Exactly. So this θ2 value in part 1. So if I measure the slope here, so basically what he's saying is that this θ2 and this θ2 have to be equal. Okay. So I can calculate θ2 using this set of equations, and I can calculate θ2 using this set of equations. That is basically this y prime value from here and y prime value here. And I can calculate y prime value at x is equal to 2L from here and x is equal to 2L from here. Both of them should be giving me the same result, same θ2. Okay. So the other equation will be θ2 from first part is equal to θ2 from the second part. Okay. So I take these equations. So y at 0 from part 1 is 0. And from there I can get C2 is equal to 0. Y at 2L and part 1 is 0. That will be used subsequently. Y at 2L is part 2 is 0. Okay. So this was the first equation. This is the second equation. This is the third equation. And then this is the fourth equation. The fourth equation is y prime at 2L from part 1 is equal to y prime at 2L from part 2. Okay. So likewise, I get 4 equations. I can these 4 equations will automatically give me the values of C1, C2 I already solved. C2 was 0, and then you can get the values of C1, C3, and C4 by solving these 4 equations. So these will give me these 4 values. Once I substitute these 4 values, I can. So for me to calculate the deflection at this location, I have to use part 2 the y value of part 2. Sorry, the y value of part 2. It's just px cubed by 6 minus 3pl x square by 2 and plus c3 and x plus c4. So c3x, c4 values I substitute. Minus 2pl by cube, 10pl cube. Okay. So basically your L is equal to 3, x is equal to 3L here, right? So that's why it becomes 10pl cube and so on. So you substitute the value of x is equal to 3L here in the equation for y at second part. Okay, and from there you'll get this equation of this value of y at particular at 3L. Okay, even if I did not value of a particular y, but I could also get an expression for y as a function of x part 1 and y as a function of x for part 2. Okay, so likewise these equations I can get, and those equations will basically give me the value, can give me the value of y at any location. Likewise y prime as well. So therefore this method is very powerful, but the problem is that it slightly takes longer time to solve. Okay, fine. Now this method is called, what is the name of this method? Double integration method, because we are doing integration twice here. So from y double prime we integrated to y prime, and then y prime I integrated again to get y. That's why it is called double integration method. So double integration method can be used for what kind of problems? What kind of structures? Which structures can it be used for? Anybody, please? Double integration method, can it be used for trusses?
No, sir.
No, right? So only flexural members, because the very definition is double integration, which means you're integrating from curvature to slope and slope to deflection. And curvature to slope and slope to deflection, the whole thing, curvature itself exists only for flexural members. Okay, that's why double integration method is applicable only to beams. Okay, or frames which are primarily deflecting in flexure. Fine. So it cannot even be used for frames which are actually compressible. Okay. Now the double integration method has been like various offshoots or derivatives of the double integration method are developed subsequently, wherein they basically consider the qualities of this double integration process, and then basically one integration equates area, the second integration in a sense means multiplication or integration of the area again, so which is basically equivalent of taking in the moment of the area. So there is several methods are developed based on that. One method is called moment area method. Okay, so can somebody quickly tell me what is moment area method? You guys have written GATE, I suppose, very recently, so you should know. Anybody? Moment area method. Nobody? There are two parts of moment area method, right?
That the change in the slope between the 2 points is equal to the area of M by I diagram.
Correct. That is first part. Very good. The second part?
Another is deflection at a point in a beam is given by the moment of M by I diagram above the point where the deflection is required.
Yeah, so you didn't quite tell it very accurately. It is not the deflection, first of all, of that point, because deflection is about some reference point. So when you just say deflection, it basically means from the undeformed location. But that's not the deflection that we are talking about, first of all. The second one is, it is not given by the moment diagram, or it's the area. It is the moment of the area about a particular point. Okay. Anybody else wants to try the second part of moment area method?
So the deflection at a particular point with respect to the tangent to the another point, sir, is equal to the moment of area between the A and B about point A, like this, sir.
Is it about point A?
Yes, sir. If a deflection want to know point B with respect to tangent A, sir.
I think, yeah, so that is something confusing. I think that is the only mistake you made. We take the moment about the point. So if you want to calculate deflections at B with respect to the tangent drawn at A, okay. So let me quickly draw it so that everybody is on board. So it is some kind of a beam, and it is deforming this way for whatever boundary conditions, moment diagram, whatever axial loads, flexural loads, etc. acting on it. So I take one point along the length of this beam, A, take another point along the length of this beam, B. I draw a tangent at A, okay, and from that tangent, how much has beam moved? Okay. So originally the beam was straight like this, let's say. So in that perpendicular direction of that, I'll measure this deflection. This will be called TB/A. Okay, so that is deflection of B from the tangent drawn at A. Okay, fine. And the method says that if this is the deflected shape, there will be some bending moment diagram that is causing this deflection, right? That bending moment diagram, let's say, between A and B, that bending moment diagram looks like this. Okay. Between A and B. So what do? I take the area under the bending moment diagram. So this is basically M/EI diagram, rather. Not exactly the bending moment diagram, M/EI diagram. So this is the M/EI diagram between A and B. I take the area of this one, from A to B. Okay. This area that is hashed here, that area multiplied by, let's say it has a centroid, that area may also have a centroid, will have a centroid. And that is at a distance x bar from point B, multiplied by x bar. And TB/A is equal to this. Okay, so this x bar is basically measured from point B, and point B is the same point where we are measuring the deflection with respect to tangent drawn at A. Okay, one second. Fine. So, and the first part, again, also if I may draw, the first part says that you draw a tangent at A, like this one, and then you draw another tangent at B, this one. The two will have an angle change or angle difference. This is that theta. Okay, you can call it theta. I don't remember whether it's called theta AB or BA, so I'll just call it theta. Theta is equal to area of M/EI between A to B. This was the first part of this theorem. Fine. So let's solve the same problem. Again, this was the problem that we just solved in the previous example. using double integration method. First span is 2L, the second span is L. The load is acting at support C at point C. A and B are the two intermediate supports. Part 1 and part 2 are the two parts. We are measuring X from here, but that hardly matters here. And what we want to do is we want to calculate the deflection at C. Okay, and this deflection is not the deflection with respect to tangent at any point. This deflection is the net deflection. So as I had shown in the previous example, the deformed shape of this beam is likely to be somewhat like this. Okay, and I want to calculate deflection at C. Now, this particular method, for example, this method that I am talking about, what we can get is TBA, which is basically deflection with respect to tangent on at a point. So if I already knew the tangent or the slope of any point, then this method would be very powerful. Okay, so if I had a cantilever and a beam extending from it, okay, and whatever type of loads are acting, from there, if I could get the bending moment diagram, I knew that after deflection, the beam will deflect this way, and I already knew the slope at this point. This was 0. Okay, slope at this support is 0. Correct? So with respect to that, if I calculate the deflection, which will be directly given to me by this method, which will be the actual deflection too. But in this particular case, that is not directly applicable. Anyway, so let me go step by step. So first I calculate the bending moment diagram. This exercise you can do yourself. So bending moment in part 1, bending moment in part 2, which is calculated. The X value here is always starting from here. Okay, so this is X is equal to 0, moving positive in this direction. Okay, so now what we need to do is, we need to calculate the areas of each part, this part of the moment, how much is the area under this moment, and then how much is the area under this moment. Also, where is the centroid of this moment, and where is the centroid of this area. Okay, so if we take a look at the moment from A to C, the whole thing, A to C, okay, the whole area will be equal to how much? What is this value? How much is this moment? PL. Okay, multiplied by total length is 3L and divided by 2. That is the total area. That is 1.5 PL squared. Okay, that is same as this 1.5 PL square. Now, where is the centroid? Of course, you can calculate the centroid. The centroid of this part, the first part, I'm calculating the location of centroid from C right now. So this whole area will not have its centroid right in the middle. Total length is 3L. The centroid will not be exactly at 1.5L. It will be somewhere slightly biased towards side C. It will be somewhere on this side. How do we do that? We will take this area multiplied by the centroid of this area, first, second part. Then the first part, its area multiplied by the distance of the centroid from here. Okay, so we will go one by one. The second part, the area is equal to PL into L by 2. That is the area. Agreed? Everybody? PL multiplied by L divided by 2. That is the total area. Okay? Multiplied by the distance of the centroid. The centroid is 2L by 3. Plus. Now, the second part. The second part will be PL into 2L by 2. This is the area of the second part. Okay. PL multiplied by 2L divided by 2. Where is the centroid located? Centroid is located at L multiplied by 1 by 3 of 2L. Okay, so this total distance is 2L. 1/3 of that. 1/3 of that will be somewhere here. So that is 2/3 of L plus L. Okay, if you solve it, sorry, 1 second. That is the. I'm trying to calculate the moment. So sorry, the location of the centroid, right? So this is the area multiplied by distance of this centroid plus this area multiplied by distance of the centroid divided by total area. Total area was 1.5 PL square. Okay. Or you did not even have to do that. It is directly giving you the moment of the area. But anyway, let's go step by step. So If you solve it, you will get 4 by 3L. Can somebody quickly check whether it is 4 by 3L? See this 2 and 2 will cancel out. So you got PL cube by 3. This 2 and 2 will cancel out. You got 1 plus 2 by 3. 1 plus 2 by 3 is 5 by 3. 5 by 3 plus 1 by 3. 6 by 3, that is 2. So 2 on the numerator divided by 1.5. So 2 divided by 1.5 is equal to 4 divided by 3. That's what you get. Agreed? Are you guys still connected?
Yes, sir.
Okay. Yeah.
Yes, sir.
So everybody is on board with this, right? So that is the distance of the total centroid from point C. Okay. And I'll show you how we are planning to solve it in a minute, but we are just doing some background work. Similarly, we will calculate what is happening between A and B. So A, B, and C, right? So between A and B, we will do the same thing, same exercise. So we will calculate the area of moment from A to B. Area of moment from A to B, as we had done before, PL multiplied by 2L divided by 2. Okay, so that is PL square. That is what this is. Distance of the centroid from B. So the centroid from B will be somewhere here at, I'll call it X bar for the time being. This will be equal to 2L multiplied by 1/3 of that. That is 2 by 3L. Agreed? 2 by 3L and PL square. Fine. So now what we need to know is how much is delta C. Now somehow the problem here is that delta C is not directly available from the moment area theorem. So we have to do some geometric manipulation. What we can figure out here is that I can find out what is TCA. TCA is the deflection of C with respect to tangent drawn at A. The tangent is drawn at A. How much is that deflection? That I can calculate. Okay. And also I can get TBA. That is deflection at B from the tangent drawn at A. So if you see deflection, real deflection at B is 0. But what I'm talking about is deflection at B with respect to tangent at A. That will not be 0. Okay. Because at A there is some finite slope, and because of that there will be non-zero deflection at B with respect to that slope, that tangent. Okay, so I can find out TBA, I can find out TCA, and if I see closely, TBA can be scaled up to get this value. Okay, so this is similar triangles, right? So TBA is part of this triangle, and there is the same triangle. If you extend, then you get this particular value. Okay, I'm not given it any name, but basically this is the so if I know this value, if I know TBA, I know this value. If I know this value and I know TCA, then I can find out delta C. Delta C is nothing but, let me call it this delta, small delta. So delta C is nothing but TCA minus delta. Agreed? Delta C is TCA minus delta, and which is again equal to TCA minus a few times whatever, some n value or some alpha value. Maybe alpha is a better name. TBA. Okay, and that alpha value will be coming from the similar triangle method. So this length was 2L. This was total 3L total. Okay, so that means this triangle, that bigger triangle, is 1.5 times bigger than this small triangle. Okay, so likewise my delta will be 1.5 times bigger than TBA. Okay, so basically I can say this delta C will be equal to TCA minus 1.5 times TB. That's what I've written here. Okay. Now, TCA would be equal to area of this moment between A and C multiplied by distance of centroid from C. Okay. So, area was 1.5 PL square multiplied by the distance from point C, that is 4 by 3 L. Now, if you notice, when we were calculating this 4 by 3 L, in that process, we had already calculated this moment directly, because when we calculated the moment, then divided by the actual area, that we got this value. So you did not have to solve for 4/3L directly all the way here and then again use it. You could have calculated the moment in that step itself, but that doesn't matter. You can go either way. Okay. So multiplying the two, this is basically your 3/2, and that is 4/3. So 3 will go away. So you are left with 2. So you are left with 2 PL cube by EI. Okay. You are just multiplying this value with this value. This value with this value. Get 2 PL cube by EI. Okay. EI I should have added here, but I had missed that. This EI is there. Similarly, this EI should be there. Okay. Moment by EI actually. I should. This all is easy. You don't have to worry about EI as long as EI is uniform. But if EI is non-uniform through the length, then you have to be careful about using correct value of EI for the respective parts. Similarly, TBA I can calculate. TBA is nothing but multiplication of this with this. That is again 2 PL cube by 3 divided by EI. 2/3 PL cube divided by EI. Okay. And delta C, as I had shown you before, is the difference of the two. So 2 minus 2/3. I think I should write 2/3 here. There is a mistake here. No, sorry. Yeah, this minus 1.5 times this. So this multiplied by 1.5 will mean PL cube by EI. This was already 2 PL cube by EI. So 2 PL cube EI by EI minus PL cube by EI will give me PL cube by EI. So that is the deflection at C, which is matching with the deflection calculated in the previous example. Okay. All right. Any questions? Fine. So quickly, we will now move to some energy-based methods. And the idea is I'm covering here mostly the methods which are going to be used frequently. Of course, there are many other methods also. Castigliano's theorem is there. And then within the double integration method, there are various smaller or intermediate methods also. But I'm not going to cover all of them. Conjugate beam method is one such. But I'm not going to cover all of them. I'm going to cover primarily the ones which are very handy and very powerful, so that we will be employing quite regularly as we move along in this course. Okay. So virtual work method. Can anybody describe to me what is virtual work method? How does it work? Somebody? Yeah. Sadullah?
So actually, we have the Castigliano's theorem, sir. Partial differential of energy with respect to load gives the deflection at the particular point. If we want to know the particular point deflection, we assume the unit virtual load and make it finally it is 0. Then we can deflection at that point, sir. That is
Castigliano's theorem when we make the deflection as 0, right?
No,
Castigliano's theorem.
Not deflection equals 0, sir. What we apply?
But that virtual load, when you make that virtual load 0, where you didn't have the load actually active,
yes,
that is basically the derivative of your energy term, right? So Castigliano's theorem says that if you take the derivative of your energy with respect to that load, that is going to give you the deflection at that point where you applied that load, virtual load. That's what you are saying, right? You take the derivative of the energy term.
Yes, sir.
That is Castigliano's method. That is not virtual work method. And that Castigliano's method has a few limitations, particularly like if you have to, that is not directly applicable to linear systems.
Okay.
I would recommend you to do some reading on that. Why it is not applicable to linear non-linear systems? It is applicable only to linear systems.
Yes.
Okay. So if there is any kind of non-linearity in the system, then that method cannot be used. The reason for that, I think, is that you equate the complementary energies. So energy. Okay, I would recommend you to read it and figure it out.
Okay, I will do it.
But that is not virtual work method. Anybody else wants to Tell us what is virtual work method?
Sir, basically, what we do is we apply a virtual load that is a not a load exists on the member. So one virtual load, for that virtual load, we'll get some internal work, and that should be equal to the external work due to the displacement in the member.
Okay. Yes. So yeah, I mean, in general, what you have said is correct, Vishal. Maybe I can just expand it a little for everybody's interest. Let me have a system. Let me start with the beam. And I have a beam, I apply a load, and let's say I want to calculate the deflection in this beam. It's a cantilever beam, easiest one that I can work with. And it is actual loads are acting in this way, and I want to calculate how much is the deflection at this location. Okay. So what do? I apply a virtual load at this point. Okay. And then what I say is that in order to understand this fully, we have to solve a few examples of how to calculate work, etc., and energy, etc. But I don't want to spend time. I am assuming that you already are familiar with all those concepts, how to calculate energy and work, etc. So what we are saying is that let's apply these loads. This is the real load, and this is the virtual load. I'm calling it R real and V for virtual. So let's say that these are applied in a sequence. Either you can say that R is applied first and then V is applied, or you can say V is applied first and then R is applied. Let me go with V followed by R. Okay, so virtual load is applied first, and virtual load you can take as 1. Okay, the value does not matter, and then the real loads are applied. Okay, now what happens is that, let's say when the virtual loads are applied, when the first part is applied, so unfortunately R is shown here first, but basically let's say only the virtual load is applied. The beam will be deflecting under the virtual load. Okay, and some deflection will be there. Okay, and in that process, let me plot the deflection of the beam with load. So this one is deflection. This is load. So when the virtual load is applied, that's a small load, let's say unit load, and you get a delta deflection. Fine. So this is V virtual. Agreed? I get a deflection delta. Fine. So what is the energy input by this load? What is the work done on the system by this load? Both are the same things, right? The energy stored or input into the system is same as the work done by that load. So that will be area under this curve. Agreed? Folks, you have to respond a little bit. So some of you may have to, yeah. Unmute your mic once in a while and just say yes or no. I can't see your faces also, right? So it's very difficult for me to get any feedback. Fine. So now the system has this much of energy built in. Then what we do is, then we apply the real load on the system. So then this system deflects further. But I did not remove the virtual load. Virtual load is still sitting and the system deflects. This is original delta. This is the real delta. Okay. So I apply the real loads. This real load is in addition to the virtual load. So this is, sorry, I plotted. You guys are not helping me at all. I was plotting it in the other direction. This is the load, vertical axis. I'm plotting the load, right? Please point out some silly mistakes like these at least. Okay, that was a mistake. I marked deflection in the vertical axis. Then the real loads are applied. Okay, and Here, of course, the real loads are distributed, or they are different kind, but I'm just trying to explain a concept. I can also substitute let me make it simpler to understand. Let it be a similar kind of a load, real load. So that is applied at the same location where the virtual load is. Let it, when the load is applied, that real load will be doing some work. And that will be this work, this area. Fine. And in the process, you will be developing an additional deflection of, or I can just start with delta plus delta. Correct? The
Yes.
load here will be, I mean, this load is R. You got R plus V acting here. Okay. Now, if you look at this thing, what is this component? You can see this rectangle, this thin strip of rectangle that I'm hashing right now. What is that? Let me use a different color. What does that area represent? Anybody? Anybody? Come on, you can see this already, right? It is right in front of you. This graph itself is showing what is that work done. Work done by what? During what?
Virtual load.
Let me put by this load during this deflection. Okay, fill in these two blanks. Somebody answered already, first part. Somebody said it is virtual load. During what?
Real deflection.
Real deflection. Very good. Fine. So that is happening because I chose to apply virtual first and then the real. If I had reversed the order, applied real first and then the virtual, then the definition of this rectangular component will change. In that case, the graph will look, you will have a bigger, let's say, component, that is a real load, and then you will have a smaller virtual. Let's say virtual is much smaller. There is no need to say that. But then this will be the rectangular strip that we will be talking about, which is equivalent to this. And that will be called work done by real loads during the virtual deflections. Okay, doesn't matter, whichever one you want to choose. So that is the work done. So what the method says is that you calculate this work done, and then that is external work done. And you calculate the same thing, internal strain energy, or strain energy simply. Strain energy is, of course, internal strain energy, again stored by or stored due to the stresses caused by the virtual load while the strains were being caused or strains were imparted or whatever you want to call it by the real loads. Two things are same. Basically, what it is saying, external work done by virtual load during the real deflection. It is also saying internal strain energy due to the virtual forces, but these are internal forces this time. So the strain energy due to the virtual internal forces, while the real internal deformations are taking place. So that's why it is just strain and stresses, which are basically another way of saying internal forces and internal deformations. Okay. So basically what we are saying is, this method is saying is that external work done. So you take this strip component of the external work and you take the same strip component of the strain energy. So likewise, you can develop one curve like this, which is for external work. I can call it W external. Similarly, you can develop a plot like this, a two-part plot like this, which will be for the strain energy U. You can call it U internal. Okay, and you equate this strip with this strip. Okay, which makes sense. Basically, each individual part is equal to that individual part. So this part will be equal to this part, will be equal to this part. This part will be equal to this part, and this part will be equal to this part. So if I compare this part with this part, it helps me solve some problems. That's why we use this part. Okay.
Yes,
That
sir.
part is clear to everyone, right? What we are comparing with what. I don't have a slide on that one. If you need, I can. But if you go to Hibbler's book, it gives a very nice explanation for this as well. You can use that one. Fine. So now instead of okay, so the calculation of this energy in the W external part is very easy, straightforward. We will see that. That is just a single multiplication that you have to do. And that too is hardly like, if you take the virtual load to be P value to be equal to 1, then that's not, there is no calculation required. However, for the calculation of strain energy, you have to do some subsequent calculations also, because if you look at the term here, it is saying strain energy stored due to the stresses caused by the virtual load, while the strains were being caused by the real load. So let's say I have a beam, okay, and what is happening is that I apply the virtual loads first. The beam has some stresses everywhere. Okay, so if I look at the stresses, it has some stress profile across the cross section because of that load at some location, at every location rather. It is varying at every location. I'm just plotting it at one location. So these are the stresses. Mark it as sigma. Then, due to virtual, okay, then I apply the real loads. Then I apply the real loads. Now this time what happens is that it gets some sigma real, but as a result of that, it gets strain real. Okay. These strains multiplied by these stresses. Okay. Stresses are virtual, strains are real. When I multiply the two, I get that component of the energy that I was talking about. Okay. And it is not just the strain versus strain multiplied by stress, because that is not really energy dimensionally. So of course I have to multiply with other coefficients, etc. But that is the crux. So then I'll get this component. Fine. So for some cases it could be basically strain multiplied by stress. Sometimes it can be internal forces multiplied by internal displacements. Sometimes it can be moment multiplied by curvature. Okay. So for a truss, it will be force displacement. For a beam, it will be moment and curvature. So you can say this is the moment that is produced, and here this you can say this is the curvature that is produced. Real curvature. So moment virtual multiplied by real curvature. Okay, and that you have to integrate. You have to integrate over the length of the beam to get the overall energy. or in other words, you can say MD. More strictly speaking, it is M multiplied by d theta real. Again, if you want to know exactly how we came to that, M by d theta is nothing but P dx, P multiplied by dx, that is d theta. So that is what it is, or in other words, it is M P P R P R dx. Okay, I often write that as d theta. Okay, you can go back to the textbook and find the explanation for that. So that is the strain energy term. Okay, this is the strain energy term, which again d theta real can be represented as phi real multiplied by dx. Okay, because your phi is nothing but d theta by dx. Okay, so d theta can be written as phi dx. That is phi dx. Then phi subsequently can be written as m by ei dx, m real divided by ei dx. That's what this is. Then you substitute the bending moment diagram because of r or mr or because of the real loads, and you will get, you can solve for u. We'll do an example. Through the example, it's much easier to follow. So I want to calculate the deflection at the free end of this cantilever beam. This is a cantilever beam, distributed, uniformly distributed load is applied. Okay, and I want to calculate what is theta at the free end. Which problem? Okay, it's being solved here. Sorry. So this is a cantilever beam. Uniformly distributed load W is applied, and I want to calculate delta here. Okay. In the next slide, we'll calculate theta. But in this one, we are just calculating delta here. So if I want to know delta here, what I do, I apply the virtual load at the same location in the same direction. So I apply a virtual load of 1 at this location. Okay, this virtual load. And what I do is I calculate the bending moment diagram because of the real loads. So this is the bending moment diagram wherein for a given x, the bending moment is Wx square by 2 and negative because it's hogging moment. Similarly, I calculate the bending moment diagram for the virtual load. So virtual load was 1 here. So because of that, I get minus x as a bending moment at given x value. Fine? Everybody is fine with this? Minus x and minus Wx square by 2.
Yes, sir.
Yes, sir.
Okay. Now, what is the external work? So external work, which component of the external work are we looking for? External work done by the virtual load while real loads are being applied. So virtual load was applied first. So the virtual load was applied first. This virtual load was applied first, and then it was still acting on the beam as the real loads are applied. And as the real loads are applied, that virtual load is riding on the beam. Correct? Virtual load is already acting there on the beam is deflected. Then I push it more. And during that process, that virtual load moves. So the work done by the virtual load will be that force multiplied by the movement. That movement is not really being caused by the virtual load because it had caused some small movement before, but that is not what we are counting. We are counting. So the beam was straight. Can you see my hands? My arm?
Yes, sir.
Yeah. So this was the straight beam first. You applied the virtual load, the beam deflected a little bit. Okay, let it be. I don't care what happened, how much deflection it was. Then I apply the real loads, and under the real loads, the beam deflects. Along with that, the virtual load also moves. Now I want to calculate how much work the virtual load has done while the beam was deflecting due to the real loads. Okay, so how do I know that how much work it has done? Because that work is basically equal to the load, virtual load, multiplied by the deflection. Okay, even though the deflection is not caused by the virtual load will still be doing a work. Okay, so that work will be equal to that delta. So this delta here is delta real. That is because of the real loads. at the free end, that delta I want to calculate. Okay, so 1 is the virtual load value. I have assumed that to be 1 multiplied by delta R. Okay, so that is the work done, external work done. That is pretty straightforward. The internal energy will require me to integrate m virtual multiplied by d theta real, or in other words, m virtual multiplied by c real or curvature real multiplied by dx. Okay, so as I showed you just a minute back, it was m virtual multiplied by d theta real, that is equal to m virtual multiplied by m by ei dx. Okay, now m virtual is nothing but minus x. Okay, and m real is wx minus w x square by 2, further ei by dx, ei dx. So that becomes the 2 minuses go away, wx cube by 2 dx, ei of course. So ei is taken out of the integration sign. Ei is taken out, you got wx cube by 2, you integrate it, you get wl to the power 4 by 8ei. That is your u value. Okay, and now what the method says is that w and u are equal. Okay, that means 1 times delta r is equal to w L to the power 4 by 8 ei. That means delta r is equal to this much. That is your deflection at the free end of a beam and subjected to uniformly distributed load. Does that make sense?
Yes, sir.
Seems straightforward, right? And the advantage with this method is that you don't have to take the derivative that you would have to do in the Castigliano's method. And plus, Castigliano's method is not as universally applicable as this virtual work method. Okay. Let's calculate the rotation also at the free end, theta. So for calculation of the rotation, what virtual load do I have to apply? Since you have all used the Castigliano's method, you must be familiar with this.
Moment. Unit moment, sir.
Yes, moment.
Yes, exactly. So we will apply moment in this direction, let's say. Unit moment, and that we will call it m is equal to 1. And because of this moment, I am again assuming it to be a hogging kind of a moment. So, I mean, if you're depending on, I mean, this is clockwise moment. So you can, if you were to account for a moment, you would call it negative moment. But what we are looking at is bending moment. So it will also cause a hogging kind of a bending moment of unit. Okay, so that is why it's called -1. Similarly, the bending moment because of the real loads was wx square by 2 negative. That was also a hogging moment. Same exercise. So I want to know how much is the theta. Okay, so this virtual load, that is moment, is applied and it is still acting, and the real loads are being applied. And as the real loads are applied, this free end is rotating. Okay, so as the free end is rotating, this virtual load, that is actually a moment, is still present, and that is also rotating. So the external work will be equal to that virtual load multiplied by real rotation. Okay, the strain energy will be equal to, again, integration of m virtual d theta real, m virtual m real by ei dx. Okay, m virtual is nothing but -1, m real is nothing but minus wx square by 2. Okay, ei is taken out, dx. You integrate this, you get wl cube by 6 ei. Okay, and that gives you theta is equal to wl cube by 6 ei. Because your w was 1 into theta, so w is equal to u, theta is equal to wl cube by 6 ei. Fine. This particular slide is not there in your lecture notes, so you can note down. I don't have to share this only this slide. You can just take some notes here. If you have taken a printout, you can just copy on that one. Otherwise, the video is anyway uploaded, will be uploaded, so you can follow from there. I wanted to give you an example of a truss structure also. So if solving or calculating deflections in a truss without an energy-based method is very, very complex, because then you have to account for various kinds of geometries, etc. And then compatibility conditions are like, it becomes a major hassle to solve a truss for its deformation values. Okay, Okay, how much deflection you are going to get, because the different members will be extending or contracting by different amounts, and then that will change the angles, etc. So, but energy method makes it very, very easy to solve deflections in a truss. Okay, so that's why we will discuss that. So you have a truss. We have already solved this truss in the past. This angle is 45 degrees. Fine. You have, so because of this thing, you have half length, that is L by 2 here. And this half length will also be, so this height will also be L by 2. It's marked incorrectly slightly, but ignore it, please. Okay, so the question is that if I apply a load P here, how much will be the vertical deflection? Calculate the vertical deflection at point P because of load P. One end is pinned, the other end is roller. Okay, so since I want to know the vertical deflection at point B, I apply a virtual force is equal to 1 at B in the same direction as P. So I apply a virtual force 1 here. And as my convention has been, I will first apply the virtual load. Let the virtual load sit there. Okay, so this is the truss, this is the top point. Let the virtual load sit here, and then subsequently the P load is applied, the heavy P load, and this virtual load 1 will be riding along as the truss is deflecting. Okay, so the external work done by the virtual load while the real loads are applied will be 1 into delta. Okay, the internal work will be equal to summation of member forces in each member due to the virtual load multiplied by the deflection or deformation of each member due to the real load. Okay, that is, you can draw the analogy here. What we were doing before, we were saying M virtual d theta real. So we were taking, if we had a beam, we were taking small parts of that beam. For a given part, we were saying how much is the moment acting in this portion of the beam, small tiny part. Okay, and then how much is the change in angle from one end to another end. Okay, how much is the change in slope for that particular part due to the real loads. Same thing I'm doing here. I'm saying how much for each member the force is constant along the member length. So I'm saying for each member how much is the member force because of the virtual load, and how much is the member deformation because of the real load. The two multiplied together will give me the strain energy stored in this member, and this strain energy will belong to, so this strain energy will be caused by the virtual loads while the real loads are being applied. Fine. Okay, so moving forward, virtual force for each member. So let's solve the truss for real load as well as the virtual load. So if I apply a unit force here, that causes a compression of 1 by root 2 in members A, B, and BC, and it causes a tension of 1 by 2 in member AC. Is that correct? That we have solved in the previous class, right? We solved a truss which was exactly the same truss. So where we found out the member forces. So these are compression. A, B, and BC are in compression. Member AC is in tension, and these are the member forces. So solving, and similarly we can solve for P. So if I apply a load P, then what will be the forces here? All the forces will be multiplied with P. Instead of 1, you substitute P. So the forces will also be multiplied with P. Okay, so I'm not writing that again. That is understood. Okay, so coming back to our definition of strain energy, that is F virtual delta real. Now delta real, that is delta because of any force, right? So delta is given by what? In order to calculate how much is the deformation in any member, how much is the contraction or expansion on any member, how can I, if I know the force value, can I calculate delta of that member?
Yes, sir.
Delta, yeah, delta will be equal to what? Force
TL by A.
FL or PL by AE. Very good. So if force is known in that member, axial force divided by A will give me the stress value. Correct? Cross section area A. So force divided by A will give me the stress value. Stress divided by E will give me what? What will it give me? Stress divided by E?
Strain.
Strain value. Yeah, strain value along the length. This multiplied by L will give me the change in length, that is deformation. Okay, so I can substitute that here. So delta real will be equal to F real. So I can say delta real is F real multiplied by L divided by AE. Okay. Now we are talking about summation of all these, summation of this expression for three members. So the three members have same AE, let's say. We have assumed the AE to be same for the three members. So AE can stay inside, but L can be taken out. Sorry, L has to stay inside because L is varying. AE can be taken out because AE is constant. So I can take AE out, 1 divided by AE out, but L has to stay inside because L is different for different members. Okay. So starting with member AB, member AB has F virtual of minus 1 by root 2. That is this force. Okay. F real of minus P by root 2, because P is also applied in the same way, so it will be minus P by root 2, multiplied by the length. So length of member AB is L by 2, L by 2. Vertical portion is L by 2, horizontal portion is L by 2. So it is L root 2 by 2 or L by root 2. That is the length of member AB. Similarly, same exercise can be repeated for member BC. All the forces are exactly identical. Length is also identical. The same terms will repeat. Plus member AC. For member AC, for a unit load, you had a member force of half. That is this. Then if I apply P here, then the member force will be P by 2. That is this. Multiplied by the length, because that's what we have. F virtual, F real, L. F virtual, F real, L. Okay, and 1 divided by AE was taken out. You add all of these, what you get is PL by AE multiplied by 1 by 4 plus 1 by root 2. Okay, that is your U value. Okay, and since we know W is equal to U, W was equal to 1 into delta, so delta is equal to whatever we got for U. Same thing. Okay, and that's how you can calculate deflection in a truss. All right. So this is the end of this chapter. I think I still have 10 minutes, but I think if I start that discussion, it will be flexibility method. That will be taking too much time. So maybe we can take some questions. If anybody has some questions, you can ask now. No questions? Yeah.
Sorry, is unit load method and virtual load method both are same, sir?
Which is the first one? Virtual work method and
Unit load method. Unit load method.
Unit load method. It's been a while since I had heard of this term unit load method. Probably it is the same as virtual load method. Let me go back and check. I don't remember exactly what was used in the unit load method. It could be the same. I'm not 100% sure.
Okay.
Yeah. But in virtual work method, you don't have to apply unit load. Basically, what would happen is that I'm assuming it to be 1 here. If you can see this slide, I'm assuming my virtual load to be 1. But even if I apply it to be V, all these terms will change to, instead of 1, I would have V, and instead of F virtual, I would have a V here everywhere. Right. So all these 1s will be substituted by V, and basically the 2 V's will cancel out.
Yes.
Let me check again once. I've forgotten which one was the unit load method. It could be the same. Okay. Anything else? All right. How was the exam for advanced steel design for those who have taken that course? The exam was okay? You had enough time? Did I ask too much? It was pretty standard. Whatever I had taught, I think I was within that domain. Any feedback? No feedback?